Glycolysis is one of the most important reactions our cells must be able to do in order for us to survive. Glycolysis is what makes our cells able to process and use energy on the scale that we need to in order to survive. It is very important to understand from a biochemistry context as well as in a medical context. And in the field of medicine, we can see the implications of how faults on the micro level can result in problems on the macro level, like diabetes. In patients who are diabetic, they lack insulin, or their cells become unreceptive to insulin, and this results in cells having the inability to incorporate glucose into the cell or import it. And because of this, it leads to high blood sugar levels, also referred to as hyperglycemia, and this has detrimental side effects. And I like to bring that up because it underlines why it is so important to understand the nuances and the minutia of this process. A lot of the reactions and individual steps that we see are very common to find in other metabolic processes. And so if you can understand glycolysis very well, you'll have a very good basis on which to understand almost all the rest of the metabolic processes of life. And to begin with, the overall reaction that occurs in glycolysis is we take in a glucose molecule as well as two NAD plus molecules, two ADP molecules, adenosine diphosphate molecules, and then we create two pyruvates, two NADH, two protons, two ATPs, and two water molecules. And so the key takeaway from this message or overall reaction is that, number one, these pyruvates that we generate from glycolysis are later used in the citric acid cycle, referred to as TCA, in order to generate high energy electron carriers or pairs like NADH and FADH2. And the reason we want NADH and FADH2 is because they will provide electrons that power the movement of protons across the membrane in mitochondria to create a proton motive force that allows us to synthesize massive quantities of ATP. And so to kind of underline this, what we see is the overall process of glycolysis isn't necessarily getting us vast quantities of ATP. That's coming later from the electron transport chain. And the electron transport chain is powered in part indirectly by glycolysis as well as the citric acid cycle. And the other thing to note is we get two protons out of glycolysis, and that's good because we need protons to create a proton motive force in our mitochondria. And another thing to note from this overall reaction is that we need to have NAD plus present. If we run out, or if all we have is NADH, glycolysis stops, and that's a bad thing. And so what we'll find later on is that our cells have developed abilities such as ethanol fermentation and lactic acid fermentation to convert NADH back into NAD plus to extract not only ATP out of it, but as well, but also NAD plus to keep glycolysis flowing, so our cells can survive. And so in the overall reaction of glycolysis, what we start off with is a glucose molecule. And the first thing that will need to happen, because glucose is a molecule that diffuses quite readily out of cells, is we'll need to phosphorylate it. And to phosphorylate something, what's going to happen is this hydroxy group will be changed into a phosphate group. And to do that, what will happen is the hydrolysis of ATP into ADP, which is a spontaneous reaction, will be coupled to this reaction that would otherwise be non-spontaneous. And so what will happen is we'll have an ATP come in, and one of its three phosphate groups will be placed onto this carbon number 6 of glucose. We'll form ADP, and this reaction is catalyzed by an enzyme referred to as hexokinase. So hexo meaning 6 carbons, and kinase refers to the class of enzymes that transfers phosphate groups. And in this case, the kinase is transferring the phosphate group from the ATP onto the glucose. And this forms a molecule referred to as glucose 6-phosphate. So we'll have OPO3 2- now bonded to our carbon number 6 on this molecule. And the rest of it will be the same. And this molecule is referred to as glucose 6-phosphate, which I shall abbreviate as G6P. And another thing to note is that this step 1 of our glycolysis reaction is catalyzed also in the presence of a magnesium 2+ ion. So this positive charged molecule helps stabilize intermediates that are created going from glucose to glucose 6-phosphate. Okay, and so I will put a 1 here to remind us that this was the first step in our glycolysis reaction. And an important final note on this first step is that the Gibbs free energy, delta G prime naught, so the standard free energy of this reaction is equal to minus 16.7 kilojoules per mole. And so what does this tell us? This negative sign tells us, if we have a negative Gibbs free energy, it tells us it's an endergonic reaction. In other words, it's spontaneous. It happens on its own. And the reason it's spontaneous is because we have coupled an ATP hydrolysis into the phosphorylation of glucose. And this is what allows us to be able to trap a glucose molecule inside our cell so we can actually perform glycolysis on it, because this phosphate group that we have here now is a lot bulkier than this hydroxy group. So once this glucose is phosphorylated, it's not going anywhere. So it's in the cell so we can continue with our glycolysis process. So going on to the next step in glycolysis, if we look at our carbons and we number them, so this would be carbon 1, carbon 2, carbon 3, 4, 5, and 6, what will happen is we're going to transform glucose 6-phosphate into a molecule called fructose 6-phosphate. And what will happen is we're going to break this bond between oxygen and carbon number 1 of glucose, and we're going to form a carbon-oxygen bond between carbon 2 and this oxygen in our ring. And another note for these kinds of structures that we see, the reason they're drawn this way is because these 6 molecule rings that we have, like in glucose, and we'll see 5-ring fructose, these are generally pretty planar, and so we will draw things either on the same side of the ring. So in this case, these 2 hydroxy groups are on the same side of the ring, whereas the hydroxy group on carbon 3 and carbon 2 are on opposite sides of the ring. And it's just because of stereochemistry and a way of keeping track of that stuff. So it's common we will draw molecules this way. It might be a little bit different from what most people are used to, but it does make things easier to keep track of stereochemistry. And so continuing, what we will see is that we'll actually have a reversible reaction as our next step, and this glucose 6-phosphate molecule will become a fructose 6-phosphate molecule, which has a 5-member ring, and the hydroxy groups stay the same as they were before on the sides of the ring. And then here we have CH2, and then OPO3 2-, as well as this new part of the molecule, the carbon 1 that was kicked out, is now CH2OH. And so it's usually easy to, or it's helpful to keep track of the carbon numbers in this. So this is carbon 1, carbon 2, 3, 4, 5, and 6. And so this new molecule is called fructose. 6-phosphate. And fructose 6-phosphate is generated via in the presence of a magnesium 2+ ion to stabilize intermediates in this isomerization reaction. And the enzyme involved is called phosphohexose isomerase. And we'll box this because that is an important enzyme to remember. So the hexose part, as we went over before, refers to it's operating on a 6-carbon molecule, so it's operating on glucose. And then this isomerase, isomers, as we remember from organic chemistry, are molecules that have the same number of atoms, but they have different bonds between these atoms. And so this fructose 6-phosphate is really just an isomer of glucose 6-phosphate. We still have the same number of carbons, hydrogens, oxygens, and phosphorus. And I will put a 2 here to remind us that this is the second step of our glycolysis reaction. And the Gibbs free energy at this point, or standard Gibbs free energy, is 1.7 kilojoules per mole. And so now we have a positive value of delta G, which tells us that this is not a spontaneous reaction. And the reason it's important for us to even keep track of Gibbs free energies is because it tells us the ratio of this equilibrium. So in the case of when we had a very spontaneous reaction, such as in step 1 previously, it means that a lot of glucose, when we couple with an ATP hydrolysis, will want to become glucose 6-phosphate. But in this reaction, we are making this molecule more uncomfortable because glucose 6-phosphate is a more stable molecule than fructose 6-phosphate. We have a positive Gibbs free energy of formation. And then the other thing to note is we have equilibrium here. And this enzyme, phosphohexose isomerase, is catalyzing not only the forward but also reverse reactions in this process. And the question is, if we want to drive glycolysis forward onto steps 3 and beyond, how are we going to do that? And the answer to that is, as long as steps afterwards are unidirectional, or we continue to consume the products, we will, by Le Chatelier's principles, push our glycolysis reaction forward. The next part of glycolysis, step 3, adds to the irony of what many people think of is the purpose of glycolysis, which is to generate ATP, in that we are going to invest another ATP molecule. We already invested one in our first step to phosphorylate glucose. We're going to again phosphorylate this molecule, fructose 6-phosphate, with a second ATP molecule, and we are going to target this hydroxy group on carbon number 1. So what's going to happen here is this reaction will be unidirectional because we are coupling ATP hydrolysis, which is a very spontaneous process with a large negative value of Gibbs free energy of formation, by extracting a phosphate group from ATP, and we will end up with a molecule called fructose 1,6-bisphosphate. Okay, and so this molecule will look like this. And this reaction is catalyzed by a very important molecule, enzyme referred to as phosphofructokinase 1. I barely made it. And this molecule is abbreviated as PFK1, And PFK1 is a very common test question you'll receive in a biochemistry class. It is commonly referred to as the gatekeeper. And the reason it's called the gatekeeper is because it kind of acts like a throttle on glycolysis and the catabolization or the catalysis of glucose. And the way it works, and the reason it's so important, is because PFK1 is an enzyme that is very receptive to levels of ATP in your cells. And so if your cell has a lot of ATP present, running glycolysis isn't going to be necessary. And the way PFK works is if there are so many ATPs present, it is likely that this enzyme will have some kind of inhibition caused by high levels of ATP present, and this will dampen the rate that PFK is active, which will slow down our step 3 of glycolysis. So I should probably do this in Roman numerals to denote it from all these other numbers. But in step 3, PFK1 is a very critical enzyme to remember in glycolysis. And because we have an ATP hydrolysis occurring, we take on a very negative value for our Gibbs free energy of this reaction, and that is equal to minus 14.2 kilojoules per mole. So we've given up a second ATP molecule to drive our process of glycolysis forward, but we've gotten this far, and the reason it is so important to have added these two ATPs is that we are now priming it, our molecule, which is called fructose 1,6-bisphosphate, which I shall abbreviate F16BP for sake of brevity. And this molecule will now have one of the bonds between carbon 3 and carbon 4 of this glucose molecule broken. So keeping track of our carbon numbers here, carbon 3, carbon 4, 5, 6, this bond will be broken between carbon 3 and carbon 4. And if we remember from organic chemistry, carbon-carbon bonds are incredibly strong bonds, and it requires enormous amounts of energy to break them, as well as form them. What happens next is the molecule fructose 1,6-bisphosphate is going to interact with an enzyme referred to as aldolase, and it will result in the formation of two molecules. So aldolase, and aldolase will cut the carbon 3 carbon 4 bond, and this results in the formation of a molecule referred to as dihydroxyacetone phosphate, which I abbreviate DHAP, and that molecule, sorry, I'm trying to keep things clean, looks like it is a ketone with CH2OH and CH2OPO3 2-, as well as another molecule, glyceraldehyde 3-phosphate. And glyceraldehyde, as the name suggests, is an aldehyde, so we have this functional group here, followed by this carbon, OH, and this other carbon bonded to the, let's slide this over, another phosphate group. So the two phosphate groups that we placed onto our glucose molecule are still here, as well as all the carbons. And at this point, I really like to number the carbons so we can keep track of all of them. So carbon 1 shows up in the dihydroxy acetone phosphate molecule right here. So this is carbon 1. Carbon 2 is this carboxyl carbon, or carbonyl carbon. And carbon 3 is this carbon here. So this is a carboxylic acid. And I'm sorry, not a carboxylic acid, but this is a ketone. And carbon 4 is the aldehyde carbon, 5, and carbon 6. So we see where all of our carbons are. We still have our two phosphate groups that we have. And let me just make sure to label this bottom molecule as glyceraldehyde 3-phosphate. And the important thing to note is that only glyceraldehyde 3-phosphate can continue in glycolysis. And consequently, we will need to convert the DHAP molecule into glyceraldehyde 3-phosphate. The final thing I will say about step 4 in glycolysis is that we should recognize the Gibbs free energy value of this reaction, and it's a very large positive number, 23.8 kilojoules per mole. And the reason it is so large and so positive is because we did just break a carbon-carbon bond, which requires enormous amounts of energy. And so, just to further underline the point, this glyceraldehyde 3-phosphate group will continue in glycolysis, and this DHAP molecule needs to be transformed into glyceraldehyde 3-phosphate. Sorry about the handwriting. And so commonly what we will see in biochemistry books is a step 5 of glycolysis, in which we actually transform DHAP into glyceraldehyde 3-phosphate. And the enzyme that is responsible for this is called triose phosphate isomerase. And this molecule gives us glyceraldehyde 3-phosphate. And so this marks the end of what many people refer to as the investment phase. And the reason it's called the investment phase is because in our effort to synthesize massive quantities of ATP, so far all we've done is supply ATP and we haven't gotten anything out of it. And what we'll see later on in the payoff phase, steps 6 through 10 of glycolysis, is the emergence of, or the generation of, our high energy electron carriers, NADH, as well as a couple ATP molecules to actually give us a positive return on investment from glycolysis, as well as get us high energy electron carriers for our electron transport chain later on. So I will end this video now, and I will make a follow-up with the payoff phase of glycolysis. I hope you guys find this useful, and let me know if you have any questions.